Okay, so there are 6 steps to the general guideline or the strategy that I have here. And let's go for step 1. So step 1, and this is really, really unlikely because it's really unlikely you're going to get a standard function to integrate, but you still need to know your standard integrals. So I've created a table of all these standard functions and their integrals, and I suggest that you learn all of these. So for example, if you're integrating x to the power n, there's the integral. And just note it's when n is not equal to -1. If you have 1 over x, the integral is the natural logarithm of the absolute value of x, and so on. E to the x integral is e to the x. B to the x, you have b to the x over ln b, and so on. These are all your standard integrals. So if you had to integrate something on this side, there's your answer on the right. All right, so those are all of your standard integrals. Now, if we don't get our answer from step 1, and again, it's highly unlikely you're going to be given just a standard integral to integrate, we need to go to step 2. Step 2 is to simplify the integrand, so the function that needs to be integrated. Sometimes the use of algebraic manipulation or trigonometric identities will simplify the integrand. By the way, integrand is the function that needs to be integrated. It's basically what appears here in between the integral sign and dx. Okay, so sometimes algebraic manipulation and trigonometric identities, it will simplify the integrand and make the method of integration a bit more obvious. That's step 2, simplify. Step 3 is to check if we can perform U substitution. If we can't do that, then we're going to go to step 4, and step 4 is to classify the type of integral that we have. So I've listed here some of the different sections that we've covered. Let's go for the first one. So we can classify it as different types of math. And in brackets, I have here Lie8. For those of you that don't know, Lie8 stands for logarithms, inverse trig, algebra, trigonometry, and exponential functions. So Lie8 goes hand in hand. It's the acronym for using by parts. So it helps you select the f of x and the g prime of x function when you are using by parts. Okay, so Lie8 is used with different types of math, and by different types of math, most of the functions you've encountered in the syllabus thus far can be divided into according to Lie8, so logarithms, inverse trig, etc. For example, let's say you have e to the x, and then you have x squared plus 7. So this is an example of an exponential function. This is an example of an algebraic function. So the a and the e in Lie8. Or so if we have different types of math, or we have products, then we may want to use by parts. And again, I'm using the word may. It's not a hard and fast rule. So we may want to try by parts. Then if we have trigonometric functions that we need to integrate, we can try using trigonometric identities and the trigonometric integration guidelines that I covered. If we have rational functions, we should perform long division and or use partial fractions and integrate from there. Rational functions, remember, these are a ratio of 2 polynomials. Then the next one that I have is circle forms. And what does circle forms mean? It's not an actual phrase in mathematics, it's just something I created to help you remember what you're dealing with. So your circle forms, and I have this table here. So what I want you to do on a page quickly is write out this table. So don't just look at it, write it out. You're going to write A, and X. Then in the next column, you're going to have minus, plus, minus. Then in the last column, you're going to have X, A. So you can see like these first and last columns, those are opposites. Then what you're going to do is you're going to put a square here, square here, square, square, square. There we go. And then last step, square root, square root, square root. So these are basically your circle forms or elliptical or ellipse forms, if you want to call it that, right? Those are where you are going to use your trigonometric substitution. So remember where you had x is equal to a sine of theta, x is equal to a tangent theta, x is equal to a secant theta, that's where you're going to have these. And I encourage you not to don't try and memorize, okay, when I have a squared minus x squared, I need to use a is equal to sine theta. Don't do that. What I suggest you do is you learn the two trigonometric identities that you need for that. So it's going to be sine squared of the variable plus cosine squared is equal to 1. And then the other one is tan squared plus 1 is equal to secant squared. So learn these two, and then when you're making your substitution for x, you can choose between which one you want. So you can get 1 is equal, so you can have 1 minus sine squared theta, and that will give you cosine squared theta. Okay, I covered that in the video on trigonometric substitution. So those are your circle forms. Those ones you may need to use trigonometric substitution. All right, so that's step 4. If step 4 doesn't help, then we go to step 5. And it looks a bit mundane, try again, but most integrals you aren't going to solve on the first time until you get a feel for integration. So you are going to come back to try again a lot. So remember that basically all of the methods of integration that we've learned, they're basically just two. They can be split up into two: substitution or by parts at the end of the day. At the end of the day, whenever we integrate a function, it's either a standard integral that we're integrating, or we're going to use a form of substitution. For example, trigonometric substitution is still a substitution at the end of the day. And the other technique of integration is by parts. So there's basically two methods of integration: substitution and by parts. And if the above steps do not assist to solve the integral, you can try substitution, like I said, try by parts, try manipulating the integral even further than you did in step 1, not step 1, step 2, try going a bit further, or sometimes you may have to use several integration techniques. Don't get stuck in the idea that, okay, it's a rational function, I'm only going to use long division and partial fractions and that's it. Or it's different types of math, I'm only going to use by parts and that's it. No, sometimes you may have to apply 2, maybe even 3 types of, or you could even apply more techniques of integration. So sometimes you may have to try several techniques of integration. And step 6, there's step 6. All right, let's start with example 1. We are going to apply the strategy for integration. All right, let's apply the strategy for integration and let's solve this example. So step 1. Step 1 is to determine if it's a standard integral. So is it found in the standard integration table? This function, x over the square root of 3x minus 1, is not found in the standard integration table. Hence, we can skip step 1. Let's go to step 2. Step 2 is to try and simplify or manipulate the integral into a form that is easier to integrate. So we have x over the square root of 3x minus 1. And a fair guess to try and manipulate this integral would be to multiply it by the square root of 3x minus 1. Some integrals were made easier to integrate when we multiplied by a square root of what was in the denominator, if that denominator had a square root. All right, so let's try this, and we'll get x into the square root of 3x minus 1 over 3x minus 1. Now, which function do you think is easier to integrate? This one here or this one here? I think that this function still looks easier to integrate as opposed to that one. So we're not going to try and manipulate this integral any further. Let's go to step 3, which is use substitution. All right, so we are on step 3. Now take a look at this function closely. I'm going to write it in this form. So I'm going to write it as x multiplied by 3x minus 1. And because this was a square root of that 3x minus 1 in the denominator, I'm going to have it with the exponent minus half. And I just like writing it in this form because it makes use substitution a bit easier to recognize. So basically what we have here are two parts. So there's the x, and then there's the 3x minus 1 to the power minus half. So when we were learning about u substitution, we learnt about outer and inner functions. Taking a look at this function here, I can see that x is my outer function and 3x minus 1 is my inner function. So an intuitive or obvious u substitution would be to let u equal to 3x minus 1. Right, so u is equal to 3x minus 1. And some of you may immediately recognize, hang on, I don't think u substitution is going to work. Why is that the case? Well, if you take the derivative of u, which is the inner function, I'm going to get 3, right? The derivative of 3x minus 1 is 3. And when we were learning about u substitution, in most cases, we had to have this derivative of the inside function cancel off with what is on the outside. Now, if you take the outer function, x, and divide it by 3, you'll get x over 3. So you're not going to get a constant, and you're not going to have x disappear. And you may be thinking, okay, let's move on to step 4. Let's go further down on the integration strategy guideline. I just want to stop you there. The purpose of substitution is, yes, to sometimes cancel that outside function, but its purpose can also be to make the integral easier to integrate. Remember, if we get this function into a form that is easier to integrate, even though we may not be able to immediately integrate it, it is still moving in the right direction. If we can make something easier, we are moving in the right direction in terms of integration. So let's just try the substitution. Let's try the u substitution. So I'm going to say let u equal to 3x minus 1. And let's get dx while we're at it. So this means that du dx is equal to 3. And take the dx over onto that side, and take the 3 over onto the other side. We're going to find that dx is equal to 1 over 3 du. All right, let's make the substitution. So it will become the integral of, well, we don't have anything for x just yet, and I'll show you how to handle that. X over square root of u, I'm going to write that as u to the half. Okay, we had square root of 3x minus 1. It's square root of u now, multiplied by 1 over 3 du. Now I see this constant here. Okay, for those of you that have been watching my videos for a long time, you know I don't like working with constants and those coefficients inside the integration symbol. So I'm taking that out there. What about this x, right? We wanted it in terms of u. What about the x? Well, I can use my substitution to solve for x. If I solve for x, I'm going to find that x is equal to, let's see, 1 over 3 into u plus 1 over 3, right? And I can write this as 1 over 3 into u plus 1. So this x on the top is 1 over 3 into u plus 1. There we go. Again, a dreaded coefficient. Let's take that out. There we go. So 1 over 3 times 1 over 3 is 1 over 9. Now, the integral that I have is u plus 1 over u to the half, integrate with respect to u. Take a look at this. Is this now easier to integrate? Can you integrate that? Yes, we can. We can just split up the numerator and divide each term by the denominator. So it will become u to the half plus u to the minus half. And can you integrate this? Yes, we can. Go back to step 1. It's a standard integral power rule. So we have gotten to an easier form using u substitution, even though it didn't look like it immediately was going to work. And the key point I want to make here is always try. Even if you don't think it's going to work, just try it. I can't tell you how many times I thought something wasn't going to work, and I just tried it, and it actually worked out in the end. So let's perform this integration. It's equal to 1 over 9 into u to the 3 over 2. We have a 2 over 3 here, and then we'll have plus, let's see, 2u to the half. Okay, so it's going to be, let's see, 2 over 27, and let's sub in x again. So u was 3x minus 1, so it's 3x minus 1 to the power 3 over 2. Then it's 1 over 9 times by the positive 2, that's plus 2 over 9 into 3x minus 1 to the power half. What are we forgetting? The plus c. There we go. And that's your answer for that question.